Hi everyone. So today's class we're going to continue our discussions on radical reactions. In particular, we're going to discuss the halogenation thermodynamics, or the delta G component of the radical reactions, focused on the halogens themselves. So if we want to determine whether a process is product favored, we have to first determine the sign of either plus or minus for delta G, right? And when we look at our delta G, right, we learned this back in general chemistry, right? Delta G has an enthalpy component, delta H, and an entropy component with minus T delta S. In a halogenation reaction, the entropy component of the equation is negligible, right? So if we look down below for a halogenation reaction, on the left we have two reactant molecules. On the right we produce two product molecules. So essentially the right-hand term of delta G, the minus T delta S, gets canceled out. So we have down below that delta G is approximately equal to delta H in radical reactions. So using the approximation that delta G is approximately equal to delta H, we can focus instead for our halogenation thermodynamics exclusively on our delta H. And we can then estimate our delta H values by looking at bond dissociation energies for the bonds by comparing the bonds broken versus the bonds made. Right? This is what we did back in Gen Chem. Everybody hopefully remembers looking at the comparisons of the enthalpies of the reactions. Right? So in this halogenation reaction here, we have methane is breaking bonds, right? We're breaking a CH bond in methane. We're breaking an XX bond in the halogen. And on the right-hand side, we're forming two new bonds, right? We're forming a CX bond, carbon halogen bond, and a new hydrogen halogen bond. And we have a table here showing some of the bond dissociation energies of relevant bonds. You can actually go back to slide 6 and look up there are a few additional bond dissociation energies of carbon-hydrogen bonds there as well, which will be relevant on the next upcoming slides. You can see it costs about 435 kilojoules per mole for a carbon-hydrogen bond to be broken. And for those of you who are following along on the slides that I posted onto Canvas, you can see that I've changed this slide around a little bit to be a little more clear about bond dissociation energies. And then on the right-hand side of the table, we have all of the different halogens. So you can see the first column gives us the data of the halogen-halogen bond. You can obviously see there's differences in the strengths, right? A fluorine bond is weaker than a chlorine-chlorine bond, which is a little bit stronger than a bromine-bromine bond, and the weakest being an iodine-iodine bond. And then if you compare the carbon-halogen bonds, right, the carbon fluorine is the strongest, and it just works its way down to carbon iodine being the weakest, and that exact same pattern is the same for the hydrogen halogen bond, where again the hydrogen halogen fluorine bond being the strongest, working down to the weakest being the hydrogen iodine bond. So we can use this data and give you some examples of the overall reactions on the next slide. You can see for this example here, right, the overall reaction where we are breaking two bonds and forming two new bonds. And if we use methane reacting with a halogen as our example, you can see for the fluorine example, the overall delta H of the reaction is minus 431 kilojoules per mole. When we use chlorine as our halogen, the delta H is minus 104 kilojoules per mole. Bromine, a little less at minus 33 kilojoules per mole. And lastly, iodine, where we actually now have a positive 55 kilojoules per mole. So you can see there's obviously a huge difference between the fluorine to bromine, to iodine, right, where fluorine releases a massive amount of energy and iodine would require the addition of additional 55 kilojoules per mole of energy to get the reaction to work. So we'll discuss the fluorine and iodine in a little bit more detail in the next slide. So in reality, right, the fluorination reaction is so exothermic that it's not practical. It's an extremely violent reaction. I know we haven't, discussed bond enthalpies, very much, so far in this class, but minus 431 kilojoules per mole is a violent or near explosive reaction. So if you were to mix methane gas with fluorine gas, shine some light on it, and you would form, fluoromethane and hydrofluoric acid, but it would be an explosively violent reaction. Whereas the iodination reaction is the exact opposite. It's endothermic, right? So it's not thermodynamically favored and actually doesn't occur at all. So you could mix these two components in a flask, shine some light on it, and your iodination product would not occur. Right, so you wouldn't form any iodination product because it would require an additional 55 kilojoules per mole of energy to be added into the reaction. So when we're talking about halogenation reactions, we're going to be exclusively focused on chlorine and bromine. Right, so chlorine and bromine are the useful halogenation reactions for organic chemistry. So let's take a little bit closer of a look at the chlorination and the bromination reactions, right? They're both exothermic reactions. So now if we use ethane instead of methane in a reaction, well, this CH bond that we're looking at here, actually, if we go back to slide 6, is worth 410 kilojoules per mole. We are breaking that carbon hydrogen bond, and on the right hand side, right, we go back to slide, I believe it's 27, the HX bond for if we use chlorine first, right, the chlorine HX bond is going to be worth 431 kilojoules per mole, and the bromine HX bond is worth 368. Oops, that's a 6. 368 kilojoules per mole. Right, so if we do the math, right, we take 431 here, we subtract the 410, we're left with minus 21 kilojoules per mole of energy given off in the chlorination reaction for the first propagation step, right? We're talking about the first propagation step, which is a hydrogen abstraction. Whereas bromine, when we do the math, right, we have 368 and 410 minus 368 gives us 42 kilojoules per mole of energy need to be added to this reaction overall, right? So the first step, chlorination, is favorable, bromination is endothermic and less favorable, requires additional energy added. Now let's look at the second propagation step, which is the halogen abstraction. Right? Now this time we're breaking an XX bond. Right? So if we have our chlorine bond, that costs us 243 kilojoules per mole, right? We have to add 243 kilojoules per mole, and bromine, we're going to be adding 193 kilojoules per mole. And on the right-hand side, we're forming a carbon halogen bond, right? And for chlorine, that carbon halogen bond releases 351 kilojoules per mole, and bromine releases 293 kilojoules per mole. So we do the math, right, and chlorine overall in this step is going to release 96 kilojoules per mole. Bromine releases 92 kilojoules per mole. We add these two together, we get 117 kilojoules per mole overall released for chlorination. And on the right hand side, we get minus 50 kilojoules per mole released for bromination reaction. So overall, both reactions are exothermic over the two-step process. But the key here is that this first step of the bromination is actually endothermic. And we can use this to our advantage, in particular when we're seeking to brominate a compound. So let's take a closer look at the chlorination versus the bromination in terms of selectivity, right? We just discussed how the bromination step is endothermic in the first step, and additionally, it releases less energy, right? It's less exothermic than the chlorination reaction. And because of that, the overall bromination reaction is much slower than the chlorination. And this leads down the path to a more selective reaction. So a bromination reaction can be very selective. So if we look at our overall reaction scheme here, right, where we have the potential energy diagram versus reaction coordinate for both chlorination and bromination, right, when we're taking and doing the CH abstraction in the first step, and we're forming the carbon radical intermediate along the way, right? That CH abstraction has a smaller activation energy for chlorination if we compare that versus the bromination, right? Where we have the CH bond here and the radical is much higher in energy. So, right, our delta E for bromination in the first step is very, very large. So that hydrogen abstraction step gives us the ability to have a much more selective overall reaction. And you can see in both cases, right, our overall delta H, right, is exothermic, where we're releasing energy from when we go from reactants to products. But the overall reaction for bromination is a much smaller overall delta H, which is being released in the reaction. So to understand the selectivity that's observed in these reactions, let's just take a closer look at the chlorination reaction. Right, so if we have something that's more complex than ethane, right, then we have multiple monohalogenation products that are possible. Right, so here we're looking at propane. We have 6 hydrogen atoms that are on the primary carbons, whereas we have 2 hydrogen atoms which are found on a secondary carbon. Right, so there's 2 possible monohalogenation products where we can abstract from either the secondary or the primary hydrogens. Right, here's when we look at the reaction down below, right, overall chlorine is very indiscriminate in its reaction, where when we take propane, we react it with chlorine and light, we get both the secondary and the primary chlorination products as products in the reaction. Let's take a look at the next slide for a little bit more details about this regioselectivity. So if we think about the regioselectivity that's observed, and we have, again, the ability to form both a secondary and a primary chlorination product, we actually get a 60 to 40% ratio of secondary to primary. And right, remember the intermediates that we're going through, we're going to have, one's going to be a secondary radical, and the second is going to be a primary radical. And obviously, the secondary radical, as we've discussed in previous slides, is going to be the more stable of the two, right? We have a more stable secondary radical. Hence, that ends up being the major product in the reaction. So if we look at least the hydrogen abstraction step, right? This is the first step. If we go back to that energy diagram back a couple steps, we're looking at the first hill of the overall reaction energy diagram, just the hydrogen abstraction step, where we're then producing the radicals out as intermediates along the way. And the hydrogen abstraction, in this particular case, you can see the secondary radical is more stable, so therefore the transition state of leading to the secondary radical is a little lower in energy, but that energy difference isn't very large, right? So we do see a slight preference for the secondary over the primary, but it's not very large, right? It's 6-to-4 ratio or 3-to-2 ratio overall. So if we compare the selectivity of chlorination versus the bromination selectivity, right? Bromination, as we mentioned, is a much slower reaction. And because of that, it's more selective for the more reactive secondary carbon atom. And you can see here when we do the same reaction where we take propane, react it with bromine, and shine light on it, we get 97% of the secondary product and only 3% of the primary bromination product. So there's much larger regioselectivity for the secondary over the primary when we compare it to chlorination. And we can use the Hammond postulate to explain this. Let's go on to the next slide so we can discuss what the Hammond postulate is in a little bit more detail. So when we're discussing the Hammond postulate, we're going to be focused exclusively on the hydrogen abstraction step because, right, that hydrogen abstraction step is the rate determining step, right? And if we recall, we discussed the Hammond postulate a ways back, right? When we talk about the Hammond postulate, we're looking at the transition state, right? Is the transition state more like the reactants, or is the transition state more like the products? And you determine that by looking at the energy of each of these. So if we take another look at the first part of our overall reaction energy diagram, right, we're still focused back here on the hydrogen abstraction. On the left-hand side, this is the hydrogen abstraction for chlorination, right? And that chlorination process, we have our reactants. We look at the transition state, and we can see the transition state is closer in energy to our reactants than it is to our intermediate, in this case, the radical that's being formed. Whereas if we look at the hydrogen abstraction on the right here in the bromination product, we have our reactants are now much further away from the transition state. And the transition state is actually much closer now to the intermediate. So you can see on the right-hand side, our transition state for the bromination looks much more like the intermediate. Right, so the overall, in this case, the intermediate being the product of that first step, the hydrogen abstraction. So our chlorination transition state resembles the reaction, whereas our bromination transition state resembles the products. So let's take a look at that transition state in more detail on the next slide to get a better understanding as to why that's important for our selectivity. So if we, again, look at these two reaction coordinates, right, the chlorination versus the bromination. Remember, we said the chlorination reaction where our transition state looks more like reactants. Right? So if we're looking at this overall transition state here on the top, our bond breaking, right, this little arrow is looking at the bond breaking. It's only beginning to break, right? This CH bond that's in this in the reaction still looks almost exactly like reactants, right? This is a very short bond here, whereas the chlorine hydrogen bond is much longer, right? It has only just begun to be formed. And so the overall radical still lies more heavily on the chlorine atom, whereas the radical on this carbon is just beginning to be formed. We compare this to the bromination on the right, right? With the bromination on the right, when we're looking at this process, the bond now is almost completely broken, right? We have a very long carbon-hydrogen bond, nearly broken. And the hydrogen-bromine bond on the right-hand side is nearly formed. It's almost completely formed. So now the radical lies almost exclusively on the carbon, where there's very little radical presence over here on the bromine side. It's almost exclusively on the carbon. And that, again, resembles the transition state now resembles that intermediate or the product of the overall first step. So when we're thinking about our transition states, the radical that's formed on the left-hand side, in the bromination step, is going to have a much larger effect, right, on the overall reaction process. So how stable is that radical will determine what the selectivity looks like. Whereas the radical that's being formed on the left-hand side with chlorine, here, this radical isn't that important. There's barely any radical present at the transition state. So let's take a look at the next slide with a little bit more detail. So in other words, what we're trying to say on the last slide is that for the bromination step, the stability of the transition state largely depends on the stability of the resulting carbon radical. Right? How stable is this carbon radical? Because that will determine how stable the transition state is. Right? Whereas for the chlorination, the stability of the transition state does not depend on the resulting carbon radical. Right? It does not. Again, because this radical that's being formed here is barely being formed. So there's not as large of an effect. And if we look at the next slide, it will understand this by looking at the overall reaction energy diagrams for each of these steps. So to understand this big difference between chlorination and bromination, right, we just need to take a look at primary versus the secondary versus tertiary radicals. Right? It's a much bigger difference for bromination than it is for the chlorination. And if we, right, you can see here the overall energy of the radical as the product of the reaction has a small effect, right? There is a selectivity, but that selectivity is much smaller because, again, the radical here looks more like the reactants. So because there's very little radical, being produced at the transition state. Whereas now we look on the right-hand side for bromination, the radicals, again, same distance and energy apart from each other as they were for chlorination, have a much larger effect on the transition state, right? And that energy difference allows for selectivity of primary versus secondary versus the tertiary, and because it no longer looks like the starting materials. So if we look at the next slide, we'll understand a little bit more detail what the selectivity looks like for a primary versus a tertiary. So in this slide, we're looking at the radical halogenation of 2-methylpropane. Right? In this example, we have 1, 2, 3 primary, right? Each of these are primary carbon atoms. And in the center, we have 1 tertiary carbon atom. And you can see the chlorination produces a very slight selectivity for the tertiary at 65% over the primary at 35%. But bromination, on the other hand, has a very large difference where bromination is almost exclusively, nearly 100% selective for the tertiary over the primary. This actually turns out to be about 1,600 times more selective for tertiary over primary for the reaction. The next slide will summarize that selectivity for all of the different reactive halogens. So you can see here, in this process, we set arbitrarily the primary carbon reaction equal to 1 and compare the secondary and the tertiary to that primary. So with fluorine, remember we talked about fluorine being a violently reactive reaction. The secondary is only 1.2 times more selective and tertiary 1.4 times more selective. So you can see the usefulness for the radical fluorination reaction is rather poor. If you have exclusively primary or exclusively secondary carbon atoms, then you can actually have a useful reaction. But if you have multiple different types of carbons, primary, secondary, and tertiary mixed in, you're going to get a large mix of all possible combinations. Whereas, right, we look at chlorination, right? Chlorination, we're going to get 4.5 times selectivity over the primary for the secondary, and 5.5 times more selective for tertiary over the primary. So you can see, if you only have primary and secondary, you can get a more reasonable amount of the desired product being secondary or tertiary, but you'll still have a significant amount of primary present in your reaction in order that you'll need to separate out from the mixture of products. Now for bromination, you can see here that number increases dramatically for secondary, right? We have 82 times more selective for secondary over primary, and as I mentioned in the last slide, 1,600 times more selective for tertiary over primary. So obviously, from a chemical usefulness of organic chemistry, bromination is going to be the more useful, just due to the selectivity that we can achieve for secondary over tertiary. Secondary or tertiary over primary, whereas chlorination will be next and fluorination almost useless. So when we think about how useful halogenation reactions are, we need to think about stereochemistry, right? What does the product look like? And one of the unfortunate artifacts that occurs in halogenation reactions via a radical mechanism is racemization, right? So when we have the halogenation of butane or anything that's more complex, we're going to usually form a new chiral center, right? So if we look at the chlorination of butane here, right, we have these two secondary carbon atoms. If we just form the monochlorination product at one of them, we create a new chiral center. Right? That atom now has 4 different substituents bound to it, so it's chiral, and we also produce the primary chlorination product, which is not chiral. So this new chiral center is formed in a 50-50 mixture of both the R and S isomers, so we get an overall racemic mixture out of the chlorination reaction when it comes to the secondary chlorination product. So if we look at the molecular orbitals of the intermediate radical, this will give us a picture as to why we're getting this racemization, right? We discussed it once earlier in the chapter, but this free radical that's formed, it can be either sp2 hybridized, right, as drawn here on the left-hand side, where we have a trigonal planar carbon with the radical found in a p orbital both above and below this trigonal planar carbon, or we can even picture it as this rapidly interconverting sp3 hybridized carbon. But again, since it's rapidly equilibrating, we're going to have a radical found at equal points in time on both above and below the plane. So we have equal probability. So no matter which molecular orbital we look at, we're going to lose our stereochemistry once a radical is formed at a carbon, even if the carbon was chiral beforehand. So to break down this step in a little bit more detail, right, this chlorination step produces, as we discussed before, the primary chlorination product, and it produces again a 50-50 mixture of the two chlorination products, both the R and the S products. This one's going to be the S product here and the R product here. So So if we start and look at the halogenation of a molecule that begins chiral, right? So we're starting with the S3-methylhexane, right? So we already have a chiral center here. That's the S stereochemistry. That center here, as we discussed before, right? This is a tertiary carbon, right? It's tertiary. It's going to be the most reactive carbon in the entire molecule, especially when we're discussing brominations, right? So that's 1,600 times more reactive than the primary carbons on the end. And, you know, what is the 82 into 1,600? You can do the math for its reactivity over the secondary carbons that are also found in the molecule. So most of the product is going to form the tertiary bromide as a product. And again, we're generating a radical intermediate at this carbon. And since we generate a radical intermediate at this carbon, we're going to racemize it and generate a mixture of 50-50 mixture of both of those products. And the reason, again, is remember that tertiary carbon is going to be the most reactive because it has the weakest CH bond. If we recall, you can go back to slide 6, right? A tertiary carbon has a CH bond strength, right? For tertiary is 381 kilojoules per mole. The secondary CH bond strength is 397. Primary is 410. Right? And so you can see from a bond strength perspective, the CH bond of the tertiary is much weaker than the secondary or the primary.